So now let's take a look at an example of looking at stagnation pressure for a physically realistic case. Let's have a sphere sitting in an airflow. The air is traveling at a velocity of 12 meters per second and a uniform velocity. It's at atmospheric pressure, and the temperature of the air is at 22 degrees Celsius. So what you've been asked to find in this example is all the places where the velocity is equal to zero. So that's the first part. And B, identify or calculate the stagnation pressure and where, if anywhere, it occurs on this flow field. So is there a place where you have actual stagnation pressure here? Maybe there isn't. And if there is a place, where would it be? So please, if you want, turn off your video and give this a try. Identify where velocity is zero, and then calculate the stagnation pressure, and then see if it occurs anywhere. Okay, assuming you're back, having successfully solved the problem maybe. Part A is quite easy. Hopefully you immediately identified that the velocity is going to be zero every single spot on the surface of the sphere. So the no slip condition, it says that there will be zero velocity everywhere that the fluid is in contact with a solid surface. And the solid surface is the surface of the sphere. So everywhere on the surface of the sphere, V is equal to zero. So that's really, really easy, and hopefully you'll get used to that. That's just a simple, super simple answer, and that is because of the no slip condition, that fluids do not slip on solid surfaces. All right, so that's baby food. On to problem, the second part of the problem. So we want to calculate the stagnation pressure. So to calculate the stagnation pressure, we know that it's made up of two components. Stagnation pressure has the ambient pressure, or the pressure in the main part of the flow, plus the dynamic pressure, so rho V squared. And in this case, P naught is equal to P atmospheric. That's pretty simple. And we know V because it was given to us. So the only thing we don't really know is rho. Now, of course, at this point, you have two options. You could use rho. The one we said is, rho for air. It's really about 1.2 kilograms per meter cubed at sort of normal atmospheric conditions. This is not truly STP. We have, we have 1 atmosphere. We have 22 degrees Celsius. That's a little bit different than the normal. But we could, so we could go with 1.2, and honestly, that would mostly be fine. If you're in the mood to really calculate it, then we can. We use the ideal gas law, and we'll do that because we need practice with the ideal gas law. Honestly, some of you are still making unit errors on that. So we're also gonna just check though that this is, that we can do this and have only one density. So the one density here, the density is gonna change as a function of pressure. We know that. So at stagnation pressure, that density could be different than it is in the free stream. But we know the condition, we've said it many times, that air can be treated as incompressible. All gas flow can be treated as incompressible if the velocity is such that you're below a Mach number of 0.3. So you're below 0.3 big M, which is speed of sound. So we hope that we are below that, but I thought it would be worth just going over that just so you get a sense for what that is. When do you have to worry about it? So the speed of sound in air, if you look this up, you can get a pretty good approximation of it that depends on temperature. It does depend on temperature, but it's only kind of weakly dependent on temperature. So here it is in degrees Celsius. So this is just an approximate formula that calculates speed of sound in air. Speed of sound in air is about 331 meters per second, and then there's a correction for temperature. If you put in temperature of 20 degrees, this comes out to be about 343. So you could use as an approximation, that in your mind, you could remember that the speed of sound in air for most of the conditions that you're dealing with, unless the air gets really, really hot or really, really cold, is going to be about 350 meters per second. So 0.3 Mach, 0.3 of the speed of sound, is about 100 meters per second. Not exactly, I know it's not really 1/3 of 350. You could say it's more like 120, more like 117. But at any rate, if you kind of have in your head 100 meters per second, if you're below that, then you're not going to have to worry about incompressible flow unless you have some massive temperature change. So if we have velocities that are less than 100 meters per second, we can treat it as incompressible flow. Of course, in this particular case, 12 meters per second is ridiculously, it's full order of magnitude less than 100 meters per second. And we can go all the way up to truly 100 and still be valid. So we are well in the incompressible regime here. So we can go ahead and use the ideal gas law and get our density, so 100 newtons per meter squared, and then 287 joules per kilogram Kelvin. So I'm using 287, so I can go from kilojoules here to joules, because joules is consistent with newtons. If I use kilojoules, I would have to use kilonewtons. It's fine to do either one. I could use 101 kilonewtons here per meter squared. I could use 101 kilopascals, and then I could use 0.287 kilojoules per kilogram. Or I could use 101,000 and use 287, as long as I'm consistent. Newtons, joules, or kilonewtons, kilojoules. You cannot mix them. You guys mix them a lot. A lot of you messed this up on one of your recent quizzes. So please get that fixed, because it does cause errors on the magnitude of a fact. It is a factor of 1,000 error, and we do not like to be wrong by factors of 1,000. I'm very, as you know, I believe engineers do a lot of approximation, and it's very, very useful to not worry about that last 1% or so, or maybe even 2 to 3%, because a lot of times there's uncertainty in the real engineering world. But a factor of 1,000 is not what we're talking about. If you're off by a factor of 1,000, you're going to probably get something seriously wrong, and someone could seriously get hurt. So please don't make that mistake. Anyway, the answer in this case is 1.19 kilograms per meter cubed, and we know that's about right. We know that usually it's 1.2, so it's a little bit less because it's a tiny bit warmer than normal. If we put in the stagnation pressure formula, then we have 101,000 newtons per meter squared plus 1/2 times 1.19 kilograms per meter cubed times 12 meters per second squared. So that's our formula. Again, I have to use newtons here. I cannot use kilonewtons or kilopascals because the velocity is in meters per second. And so that's going to give me kilograms and meters, not kilometers or whatever that would be. So I have to do that. When I do that, I find that the stagnation pressure is 101,000 newtons per meter squared plus 85.68 newton per meter squared. So that's not a big number, 85, compared to 101,000. So technically the answer is that the stagnation pressure, if you carry all those sig figs, would be 101,086 newtons per meter squared. But in truth, of course, that's getting down to a lot of sig figs, down to the 5th and 6th significant figure there. So, it really almost didn't make any difference. So the stagnation pressure in this case, with a velocity of only 12 meters per second, and air, which has a very low density. So here's our density right here, causing this to be a pretty small change. If this were water, of course, it would be 1,000 times greater. So you would see a much larger change in the stagnation pressure from the regular pressure if you had a more dense lit fluid, like a liquid. So that's something to be aware of. That in this case, it was a pretty small change, really almost a negligible change in pressure. Where does it occur, this stagnation pressure? Well, the stagnation pressure is going to occur where the flow goes to zero velocity without significant viscosity effects. And, it's not here, right? That's no good. The flow should just zip right by there and have, the same velocity it has here. But viscous effects are going to cause it to go to zero here as this fluid gets dragged by the slower moving fluid. So that's going to be a place with no stagnation pressure. It's going to be probably just right at this pressure. This is going to be the same down here. Now the only place where you have stagnation pressure is right here on the true front of the sphere. Right here, that would be the stagnation point. And that's where you would expect to see the stagnation pressure. And really, as you move away from that stagnation point, you're having increasing viscous effects, and you'll be farther and farther away from that stagnation pressure.